Welcome back, everyone. Today is just a follow-up video for last video on the complicated yet beautiful way of linear algebra's notation, right? It seemed a bit complicated, describing complicated, describing simple subjects in a complicated format, but in reality, it just gives us a broad definition of more complicated things like higher dimensions of space, four dimensions and up. So today we're just going to briefly discuss vectors, and it's just this brief intro to vectors. Probably won't take up very much time, hopefully. It should be fairly simple. So let's just say vectors, right? Now vectors may sound familiar from physics, right, and other fields. Something that has a magnitude and direction, and scalars, something that only has a magnitude but no direction, right? And today we're just going to discuss some, just the pure mathematical vectors, which are also used in physics, right? We're kind of going to be describing vectors, showing how to describe vectors in this video. Purely math in this case. Now, later on, we'll definitely do physics, of course. That's actually the field that I'm most interested in. But I love math as well. Anyway. So what should we get started with? So, first of all, we're defining vectors in R, vectors in Rn. Okay, so this just means that vectors, this is just a broad definition, so these vectors can be vectors in 2 dimensions, 3 dimensions, 4 dimensions, 1 dimensions. We're just giving a broad definition to what these vectors are, and they have to be real numbers, right? They can't be complex. So you can express vectors in rows or in columns. You can express vectors like this. You can have, this can go on, let's do xn, right? Or you can also do the same thing for in this format, right? This is just human convention. Depends on the situation, actually. Certain cases, we'll discuss that in the future. But for now, I actually want to focus on the column vectors, or describing vectors in columns, right? And that's probably what we are most familiar with, since I've discussed this in the past videos on matrices. So why don't we say we have a vector v, right? Bolded v, that's crucial. Just to hit the point on that it's v, we can have a little directional symbol up here. Let's say that's equal to, we can have infinitely many in here. So we can have v1, v2, it's going to go on to vn. And these are all just components. All of these are components of this vector here. So in this case, v1, v2, vn are all, why don't we just write this, are all members of the real, just to refresh your mind. They're all members of the real, and they're all components. Components. You could just write that this is just essentially equal to v, our bolded v, all components of v. Right? Okay. So why don't we just hit the point home? It should make sense by now, but you can also, let's say we have another vector, I don't know, c, or let's say it's vector n, Okay. Vector n. Or actually, this might look familiar if you're into physics. Vector, actually no, that would be a pseudovector. I was about to write vector B, magnetic field. But if you know a lot about physics, you'd know that that's a pseudovector. So let's write vector E, electric field, all right? And then we can have, we don't have to have n components. We can just have, E1, E2, E3. Maybe this can be expressed in three-dimensional space, right? So yeah, these are all, and again, these are all just, this vector has three components, right? E1, E2, and E3. So what else can we discuss here? So why don't we just start defining vector addition? Vector addition. So let's pick out two vectors, vector A and B maybe. So vector A and B. So let's set A equal to, just to point them that that's a vector. We'll put directional sign above it, of course. So we have, A has, n components, A2 all the way up to AN, right? Right, and B also has n components. B1, B2, Bn. Okay, so let's say we want to add these two vectors, which are also column vectors in this case. So what is this? Well, all this is incredibly similar to matrix addition. It's essentially just adding term by term like this. So this is the exact same thing. This is convention. This is the exact same thing as, essentially the same thing as when, matrix addition, like we discussed in the very first video. So this would be our new matrix. This would be our new matrix all the way up to A and Bn. So yeah, that's simple, fairly simple if you watch the first video, hopefully. And in general, it should be quite simple. And let's use some actual scalars let's use some real components instead of just these variable components of A and B. So let's say we have two column vectors, C and D, and we want to add them. Well, let's say C is equal to, let's make these two-dimensional vectors, right? Vectors in R2. Four and -6, right? And then D can be equal to 5, -1. Okay. So now let's say we just want to simply add C and D. So we can write this as 4 plus 5, and -6 plus -1. Right? Just combining these vectors into one matrix here. This can be simplified into 9, -7. Right, and this is just A, and this is equal to, this is just C vector c plus vector d, right? That's all this is, right? So now let's just take a look at, briefly take a look at scalar multiplication. So the scalar multiplication, right? So scalar, as we said earlier, it just has a magnitude, so it's just any real number, right? It's not a vector. It's just any real number. And so we can have scalar. Let's say scalar x, right? Scalar x. This can be our scalar. Let's say we want to multiply this by the scalar by vector, I don't know, vector q. And this, what is this? Well, we're not going back again. We're not going to go back to all of this complicated dot product. This is actually very simple, and we've covered this in our inverting 3x3 matrices, 2x2 matrices part on this channel. So what would this look like? First of all, let's just define vector q. I'm gonna give you a broad example, and then I'll give you one example of using actual real numbers instead of variables. It's like q equal to q1, q2, q3, q4. Okay, 4-dimensional, right? And then let's say we want to multiply x by this. So x times q1, q2, q3, q4. And this is actually just equal to, you can think of this as the distributive property. It would be even easier to see this if this is in row form. So all this is just x times q1, x times q2, x times q3, and it goes down to x times q4, right? And this is equal to x times the vector q, right? So that's all this is. So now let's use let's substitute values for those numbers, for those scalars. Okay, we can use okay, we'll use different values here. Let's have the scalar -3, okay? -3, and let's have that multiply that by let's say beta vector, okay? Beta. And beta should be bolding these vectors, right? And beta can be equal to, let's say, maybe, let's keep this in 3 dimensions here. -2, 4, 5. Yeah, okay, that works. Okay, now we're multiplying this by the scalar. So you just distribute the values over here. -3 times -2, -3 times 4, -3 times 5. This is your new, this is -3, the scalar -3 times the vector beta. And this can be simplified to 6, -12, and -15. Okay, and that is about it for me today. Hope you guys enjoyed, and have a nice day. Hopefully I'll be uploading another video tomorrow. So thanks everyone for watching. Bye bye.